Hello students, today we will continue Gauss divergence theorem. We have already studied that how to verify Gauss divergence theorem. Now we will see second example of Gauss divergence theorem, that is evaluate double integration f bar dot n cap ds for f bar is 4x I bar minus 2y square j bar plus z square k bar, where S is curved surface of cylinder x square plus y square equal to 4 bounded by planes z equal to 0 and z equal to 3. Now this is second type. As I told you, there are four types of four types of examples on Gauss divergence theorem. That is second part here, evaluate surface integral. Now if you refer first problem and if you refer this surface S3, then it was curved surface of the cylinder, and if we follow this same technique that we have followed for S3, we can solve second example where cylinder the equation is given as x square plus y square is 4 bounded by the planes z equal to 0, z equal to 3. Because in first example basically we have calculated surface integral as well as volume integral. So you can refer previous problem for finding solution of problem number 2. That was second type. Now third type is the examples which include vector identities. Consider third example, prove that triple integration dv upon r square is double integration over s r bar dot n cap upon r square ds, where volume bounded by closed surface S. Now since S is closed surface, by divergence theorem we can say double integration f bar dot n cap ds is equal to triple integration del dot f bar dv. Now consider f bar is r bar upon r square. Now we know the vector identity del dot phi u bar is del phi dot u bar plus phi del dot u bar, where phi is a scalar function and u bar is a vector function. Now we can easily observe that here 1 by r square, that is r raised to minus 2, is phi and r bar is here u bar. So if we compare these two, then by using this vector identity we can write del dot r bar upon r square is, this is nothing but del phi dot r bar plus phi, which is 1 by r square, del dot u bar means del dot r bar. But we know that del is a differential operator. So if we operate del on r raised to minus 2, then it will be minus 2 r raised to minus 4 r bar. Because we know del of r raised to minus n is like this. So here there is nothing but derivative. This is differential operator. Now dot product with r bar. Then 1 upon r square into 3, because del dot r bar is always 3. Now if you solve this, if you simplify this expression, then it is 1 upon r square. Now from equation 1, that is by Gauss divergence theorem, if we put this value in Gauss divergence theorem statement of the theorem, then double integration r bar upon r square dot n cap ds is simply triple integration 1 upon r square dv. Okay, since this is divergence of the this function, del dot something means divergence of that vector field, that term. Now next example, fourth example, here it is a sphere. So we will use spherical polar coordinates here, since the surface in next example is x square plus y square plus z square is a square, surface of the sphere. This is what you have to evaluate: double integration x square y cube I bar plus z square x cube j bar plus x square y cube k bar dot ds bar. Again, by Gauss divergence theorem, we can write the statement f bar is here, the vector given in the problem. Del dot f bar, if we calculate, it is 2xy cube. Now transforming variables to cylindrical polar coordinates, this is how we can write x y z and dx dy dz. Next thing is r varies from 0 to a, theta must be from 0 to pi, and phi must be 0 to 2 pi. So if we substitute all these values here, and if we integrate with r, with theta and with phi, then integration will be 0 by the standard formula of integrations. The answer will be 0. So this is how we can solve 4 types of examples on Gauss divergence theorem. Thank you.